I think it's yeah, sounds good. Yes. Maybe we first mute. Yeah. Okay, so I will go. Hi everyone. We are glad to welcome Ravi to give the talk titled "Towards Influence-Aware Safe Human-Robot Interaction" today. So Ravi is a fourth-year PhD student in RI at CMU, advised by Changliu and Andrea. His work focuses on the intersection of safe control human-robot interaction and learning for robotics in order to make safe, adaptive, collaborative algorithms for robots to work with people. He holds a bachelor degree in EECS from Berkeley and is a recipient of the NSF Graduate Research Fellowship. So let's welcome Ravi to start.
Cool. Yeah, so thanks for having me. I'll be talking about some of my work on influence-aware safe human-robot interaction. So, first let's talk about the fact that people are actually being influenced by algorithms every single day, whether it's through YouTube recommendations, Google search, TikTok, Facebook, or even chatbots like ChatGPT. These are all interactive systems that have direct influence on the kind of things that people are seeing and talking about daily. And what I'd really like to focus on is the fact that we know that these algorithms can have long-term influence on people's lives. And we've particularly seen a rise of polarization as a result of misinformation, which can be a big safety concern for the mental and physical well-being of people interacting with these systems, because if they act on incorrect information, they might end up harming others. But what we're here, of course, for robots, and robots are actually getting increasingly common in real-world scenarios like autonomous driving and manufacturing. Waymo actually says that in 2023, they took 700,000 people on rides. And so robots are really only going to get more common from here. And just like algorithms and recommendation systems, robots will also inevitably influence people. So you can see here on the left, there's a video of one of my collaborators sort of moving away from this robot as it does something unexpected. And on the right, you can see a video of this hospital robot from a company where a person in a walker actually needs to move out of the robot's way. And this is like maybe not something that we want the person to have to do. And what I mean here is that it's really important to be careful about how we design robots so that they safely and positively influence people. So the key question in a lot of my work is how can we formalize safety in influence-aware human-robot interactions? And the key idea that I'll keep coming back to is that safety analysis needs to consider both the physical and latent intent dynamics of the human and robot. So a lot of my work falls into these two general buckets. First on safe control with human models, and the other on influence-aware human-robot collaboration. And I have a bunch of papers in both these sections, and I'm currently working on sort of joining them to do the full influence-aware safe human-robot collaboration problem. So in this talk, I'll be talking about one sort of safety-related paper, one influence-related paper before jumping into the full influence-aware safety problem. So first, let's get a good understanding of the problem statement here. The robot has some objective denoted by J. In this simple case, it might be block picking. It is subject to some physical dynamics, so the robot's control input will affect how it moves around in the world. And classically, people have thought about doing this kind of problem with physical safety constraints. Maybe you want to keep the end effector of the robot away from the table. And there's been a lot of work in this regime. Basically, you're trying to compute safe control strategies for robots like drones or legged robots to guarantee that they don't collide with things and they don't fall over. More recently, some researchers have started to include a human in this loop, which means now your physical dynamics also include the policy of the person, and your safety constraint is now with respect to the person because you don't want to collide with people. And there's been some work here at CMU thinking about how to do this kind of collision avoidance with people. And there's even been work from some researchers at Berkeley from a few years ago where they model people as having a goal, and the robot wants to stay safe with respect to the trajectory of the human that has some goal in mind. And in this talk, basically, we'll refer to the person's goal or their intent generally as this vector Z. And we want to be understanding how Z influences safety over time. So there's something additional that we really know about people. Specifically, that's that people can be influenced over time and that their intentions can also change. So what we should really be solving is this problem, where we additionally have this F sub Z that denotes how the intention of the person will change over time, specifically as a function of both the human and the robot. So in this picture, that's denoted by the robot's policy pi r influencing the human's intention ZH over time. And actually, this full problem has not really been studied in the literature, even though this is kind of what we would ideally want to do. We do have some hope because people have done this work just without this safety constraint. So thinking just about how can you develop models of people that account for the influence that the robot has on them. And so there's been some work from Stanford or Virginia Tech on this, learning this as latent intent dynamics of multi-agent interactions. And of course, there have been a lot of papers in self-driving literature thinking about this problem of influence on other agents. But in my work, what I focus on is this full problem of influence-aware, safe human-robot interaction, where here we've added 2 additional constraints that just say that the human and robot need to pick dynamically feasible control inputs. Yeah.
Is F also depends on human intent and human state?
So you're saying F sub X?
No, I mean the category for F, the unsafe.
Oh, yes. So that in general is just defined with the physical state, not the intent state. So like you just want to make sure that 2 agents are not in collision. And so your failure set will just be like a function of the physical state X and not necessarily of Z, though Z will like influence X over time.
Gotcha.
Yeah. Yeah, so I guess one question is, why is this formulation interesting? Basically, the idea is that the intentions of the agents will affect how safe you can be. So if you're really confident as a robot that you can change the human's intentions, the robot can be less conservative. And on the flip side, you want to be certain that your robot's not overconfident about its predictions to the point of becoming unsafe. So first, let's motivate a little bit why we think about this as a safe control problem. Specifically, like, why do you even need safety? We can't just tell robots to not collide with people. And let's take some inspiration from this video here. Here we can see a biker going through a forest pretty fast, which is very impressive. There comes a point where it looks like they're going to collide with this tree. You can see that if they just sort of continue on their nominal path, they might actually collide with this tree. But you actually could choose different trajectories that take you around this obstacle. And you can see in the video that the biker chooses to go left. But let's rewind a little bit to this moment here. So the question really is, why did the biker need to make a decision on which direction to steer so early relative to them actually colliding with it? And the reason is that it needed to account for the dynamics of the system, which is one major reason why safe control is really non-trivial. The second is that safe control gets even harder if there's uncertainty in your environment. So let's say maybe you think that the tree is a little farther away than it actually is. This might mean that trajectories that were previously safe are actually unsafe under uncertainty. And finally, there might actually be other agents in this scene. So if there's another biker, they might have their own intentions. And so this makes it even harder to know what to do and how to stay safe. So let's think about sort of the simplified version of this problem, where we just have some set of states that we want to avoid. We'll call that the failure set F. And basically, if we account for the dynamics of this system, we can compute all of these states such that if the bike enters, or if our agent enters this extended set of states, then no matter what they do, they will enter the failure set at some point. And this is sometimes called the backwards reachable tube of F, or the inevitable failure set. So one question is, how can we actually encode safety mathematically? And basically what we rely on is this idea of a value function that tells you whether your state is safe or unsafe, whether or not it's in your inevitable unsafe set. And we want to ensure that no matter what state the system starts in, it'll get safer over time. And this can be thought of as this sort of energy dissipation constraint, which is written out mathematically on the right. We're saying that the time derivative of the value of X should get should be like upper bounded by some value denoted by eta. So starting from some unsafe state in this depiction, it might mean that you sort of roll down this hill and end up in a safe state over time. So one big question is like, how do you actually get this magic value function? And this really is like the big question in safe controls. In general, this will be synthesized offline for a particular dynamical system. And the second question is, how do you actually compute safe controls based on this like energy dissipation constraint? So in a lot of the work that I'll be talking about, we will encode this as a set of safe controls where you'll pick all the controls that satisfy some like modified version of your energy dissipation constraint. If you're curious, actually, this is specifically if you have a dynamical system of this control affine form, which means that f and g are nonlinear functions, but u enters like affine in an affine way into this equation, you can write this out as a linear constraint on u, where here the notation LG V and LFV mean the Lie derivative of V with respect to f and g. So now that we have sort of a foundation for safety, I'll start talking about one of my projects in multimodal safe control around people. So if we go back to our full influence-aware HRI problem formulation, we're going to not jump fully into this yet, because we're not ready to solve the full problem. So we'll make one key assumption where we remove the dependence on the robot's control inside the dynamics of the human's intention. And specifically here, we're focused on the scenario where we have multimodal uncertainty in the human's policy. And when I say multimodal, I mean like in the sense of a bimodal probability distribution and not like vision versus language. So we're going to ground this in sort of a human-robot interaction domain where the two agents are trying to reach different goals. So there's multiple potential goals for the human denoted by this variable z, and there's this additional goal for the robot denoted by z sub r. And the robot needs to keep a belief over the goal of the human because it's really not known to the robot a priori. And additionally, because people are not perfectly rational actors, there'll also be some noise in the human's dynamics. So this is really naturally modeled as a mixture of Gaussians because we have uncertainty over the discrete mode of the human, which is their goal, and there's uncertainty within each mode, which is because of the dynamics. So before jumping into safety, we'll write out our dynamical system. So in this case, we're going to think about the joint human-robot system. And it has this form where the f function contains both the robot's f function and the full dynamics of the human. And the g function contains only sort of the g function of the robot because the robot's control doesn't have any direct influence on the person. And additionally, we can write out our sort of multimodal Gaussian assumption here. So we'll note that because we have uncertainty in the human, we actually have uncertainty in f and specifically no uncertainty in g. And so now we're going to think about how we can actually synthesize safe controls under this sort of multimodal Gaussian assumption over f. So the first thing we do is assume that we already have a v of x synthesized and that it's valid for all of our modes. For example, if we're doing this in human-robot interaction, you might assume that there's some maximum bounded velocity for the human and synthesize your safe control with respect to that like worst case scenario. And we'll remember that we have this safety constraint that we want to satisfy. But because we have uncertainty in the human, this means we have uncertainty in f, which means we actually cannot directly satisfy our control constraint. So instead, we'll do our best and try to satisfy this probabilistically. So we'll impose a chance constraint, meaning that we want the probability of the original constraint being satisfied to be greater than or equal to 1 minus epsilon, where epsilon is some small number. And the big question in this work is how do we compute a least conservative safe control that satisfies this chance constraint? And I really emphasize least conservative here because you might imagine that it's sort of trivial to say, we don't know what the human is going to do, we're just going to run away from the person. But because the robot actually has its own task to do, you want to make sure that you're least conservative with respect to this. So let's start a little simpler. We can actually say that for a particular form of f and g, we can plug in all of our values and get this sort of linear constraint in u that is now a function of our model f of x. So we can sort of draw this out. And on the left, you'll see the human model space. So any dot in this space denotes a particular f of x. And on the right is sort of the control space for the robot, which corresponds to like what controls are safe or not. So every point in this space f corresponds to one constraint in our control space for the robot. And in general, what safe control will do is you'll take some reference control that is potentially outside of your set of safe controls and then project it to the closest control input that is actually inside your set of safe controls. So remember, we were talking about this as a normally distributed human model. So let's say you have a distribution of potential values of f. Every one of these values will give you a different constraint. And because the sort of support of a normal distribution is unbounded, this means you have an infinite number of constraints. So we can go back to our chance constraint and say, okay, we instead just want to stay safe with respect to this bound where 1 minus epsilon denotes all of the possible models that have like 1 minus epsilon probability, and stay safe with respect to only those. So in particular, you can actually compute the worst case model that gives you the most restrictive constraint with respect to this 1 minus epsilon bound. That can be computed by a simple optimization program where you're trying to find the value of f that maximizes this constraint value such that the cumulative distribution function is equal to 1 minus epsilon. And this gives you specifically one constraint in your control space, which is great because now we can be safe with 1 minus epsilon probability with respect to this sort of unbounded Gaussian distribution. But remember, we were talking about this in the formulation of multiple potential modes for the human. So, this means that we might have a multimodal Gaussian where we want to stay safe with respect to all of these modes. And we looked into the prior work and found that basically like previous approaches are all thinking about this in the unimodal setting. So you only think about like one unimodal Gaussian distribution that you want to stay safe with respect to. And so the easiest way to map that onto our setting is to say, if we have some belief over the mode of the human, you pick the most likely mode and say that we just want to stay safe with respect to that mode only. And there's some other work that deals with unimodal safe control, but is instead thinking about bounding all of your potential uncertainties into a single ellipsoid. So this means that you'll pick like the worst case bound with the worst case model with respect to this joint ellipsoidal bound, and then pick the safe control based on this worst case bound. And this might be like overly conservative because you're picking, because you're like grouping all of your uncertainties together. So for a slightly less conservative baseline, we introduce a naive multimodal solution, which is a very intuitive like intersection of all of your 1 minus epsilon constraints per mode. And this is one of our baselines that we're comparing to. So what we do in our work is actually understand that there's some freedom that we have in choosing these epsilon bounds per mode because we have this belief over which mode is actually the true mode of the system. And so what you can do is pick your epsilon such that you actually balance your constraints in the control space such that they're all equal, and then stay safe with respect to this. And you can show that this is still a safe control, but is not overly conservative. And basically the way we do this is by posing an optimization problem where we first will find sort of the worst case mode for every pair of modes, or the worst case model for every pair of modes, find the two modes that sort of maximize this difference, because in general, we have more than 2 modes of the system. And then you can choose your epsilon that minimizes this maximum difference, which means that you'll balance all of your constraints. And if you make this subject to your original chance constraint, that means that you can compute your worst case model that gives you the same constraint in all modes. And I know this is a lot of math, but basically the idea is just that we can formulate an optimization program that gives us the solution to our constraint balancing problem. So let's go back a little bit to our problem formulation where we had this safety with multimodal or a mixture of Gaussians. And we basically run simulations in this simulated domain, comparing our unimodal method, our naive multimodal method, and our proposed multimodal safe set algorithm, which is our constraint balancing method that we just saw. So here you can see a video showing like what the actual simulation environment looks like. The robot is this red agent that's moving between its goals. The human is here in blue. It's also moving towards its goals. And you can see when we measure the safety rate, like what percentage of all states in the rollouts were safe, Actually, all three of the methods are pretty good at staying safe. And we can see that this naive multimodal algorithm, which we would assume to be slightly more conservative, actually ends up being the most safe. And secondly, we're interested in the efficiency of the system. So we're measuring how many goals are reached by the robot in all of its rollouts. And you can see that the unimodal safe control lets the robot be like the most efficient versus naive multimodal safe control, which is the most restrictive. So it decreases this like number of goals reached versus our proposed method is somewhere in the middle. And finally, we measured the size of this like actual safe control set. And you can see again that unimodal safe control keeps this control set the biggest versus the naive method, which keeps this the smallest. So you might be thinking like, okay, it seems like unimodal is good enough, like it gets pretty good performance and is still pretty safe. And this is basically because doing this task in general, like the nominal control, is actually already quite safe. So even just a simple unimodal controller gets us above our desired safety threshold. And the key idea here is like safety critical scenarios are a very long tail event in these kinds of simulations where there's a lot of free space. And so we know that safety itself is actually very context dependent. So to get a better understanding of the actual safety of these different controllers, we changed the nominal controller instead to just follow the human around. So you can see here in these videos, now the robot is no longer thinking about its own goal, but just trying to follow what the human is doing. And on the left, you can see a video of the unimodal safe control versus our algorithm on the right. And actually now you see a very big difference between the three methods. And you can see that the nominal controller is actually only safe like 20% of the time, which is really like tells you that this is a very different kind of situation than the last simulation. And now unimodal safe control basically ends up violating our minimum distance constraint, which is denoted by this dotted black circle. And basically anytime the human changes its mind. And this is because you're sort of not accounting for this possibility in the safe control formulation versus our method that is able to stay safe with respect to our desired level of safety.
So the human intent dynamics is learned as a GMM model.
We're not learning the intent dynamics here. We're just saying like there is an intent for the human that we're accounting for like all the possibilities together. Yeah.
So you already have a kind of you already have one truth model. Which is always two models.
So we don't have access to the like ground truth human intention. We're keeping a belief over what the human's intention is over time. All we're saying in the multimodal case is that you're going to assume that like your belief gives you a probability over which intention is possible.
And the belief update is done by some Bayesian system.
Yeah.
Bayesian, the GML on top of GML model.
So the Bayesian inference gives you the mixture weights on the GMM. Yeah.
By the way, how do you simulate this?
This is just a
policy or
so yeah. So the human is just like a simple like goal reaching like double integrator and has some noise added to the control input.
Gotcha.
Yeah.
Thanks.
Yeah. So one question you might have is whether this Gaussian mixture model assumption about the human is actually too restrictive to use for real world applications. And this I think is a fair question. But let's look at some recent pedestrian prediction models that have seen a lot of success in the last few years. And if we zoom in, you can actually see that in the architecture, they're predicting a GMM prediction or the GMM parameters of a human. And this is a great sign because it basically tells us that this multimodal safe control approach would be compatible with these learned models of people. And I haven't actually like done this, but basically the idea is that it is feasible. So now I'll jump into a project on the other side, thinking more about the influence-aware human-robot collaboration problem. And the first question here is, how do we actually get influence-aware models? So really, people have thought about this primarily in the self-driving domain. So companies like Uber and Waymo have built these models like their conditional behavior prediction or Uber's lookout model, where you're trying to understand what the other agents will do as a function of your ego agent's future plan. Basically, you want to understand, like, if I take this left turn, how will the other agents react, and do that kind of reasoning. So the way that you actually get these models is basically through an insane amount of data. Waymo's model was trained on 18 years of continuous driving data, and Uber's Lookout model was trained using about 1 million frames of LiDAR. So these kinds of data sets are not always available in the human-robot interactions that we're necessarily interested in. And in general, influence-aware models may lie anywhere on this spectrum, where on one side you have very data-driven models like conditional behavior prediction or CBP from Waymo. And on the other side, we might have very structured models that come from something like game theory. And we can also put some work using latent intent modeling on this spectrum that's seen some success in playing multi-agent games, sometimes with people. But in our work, we introduce our method called model-based CBP, or model-based conditional behavior prediction, that doesn't prescribe as much about the humans as a game theoretic model might, but also doesn't really require this giant pre-existing data set for the interactions that we're interested in. And specifically, we're interested in extending the CBP idea to scenarios where we don't have giant data sets, like in collaborative manufacturing or home robotics. So if we go back to our influence-aware safe HRI problem statement, in this project, what we're going to do is think about two things. First, how do we construct this objective function for the robot? And still thinking about this scenario where where we have a set of discrete goals for the human that we're sort of estimating online, instead of assuming that Z is some arbitrary learned representation. So basically what we do is think about conditional behavior prediction with goal states. So in this depiction, this human has a set of potential goals that we don't know which one they're going to pick. And what you could do in general is estimate one of two things. First is what the human would do in isolation. So, or basically what they do based on the history of what you've seen them do to this point. This human might pick this goal Z1. Instead, what you might want to do is predict what the human would do when the robot is also present. So for example, if the robot is going to pick this goal Z1, then the human might actually react in turn and pick a different goal instead. So the key idea in this paper was that we separate the inference of this prior goal and the posterior goal, which we denote as ZH prior and ZH post. So there's been a lot of prior work in HRI that's done this sort of observational goal prediction, where you're just trying to figure out what will the human do based on the history that you've seen. But in our work, we introduce an additional conditioning on the future goal of the robot, denoted by ZR, so that you can get a conditional model of what the human will do based on the robot's future choices. And here we similarly look at this problem in a 2D simulated manufacturing setting, where the human's state is XH in blue, the robot state is in red, and all their goal states are in green. So we can think about, if we have an influence-aware model that is specifically our model-based CBP method, how do we actually utilize that in interactions? So the first thing you can do is say, okay, we actually want to influence the person to become more efficient at this task. So naively, if the robot just picks the closest goal to itself, the two agents might pick goals something like this. But with the model-based CBP, you can actually proactively influence the person to choose a more efficient goal for the team. So in this simulation, the robot moves over to the left. And at this point in time, the human is like, okay, I see that the robot is going away. So I actually fine to choose this efficient goal for the team. On the other side, you might actually want to be very courteous to people. So you want to make sure that the robot understands how it will influence people in the future, and say, I actually don't want to change what the person wants to do. So naively, again, the robot might choose a goal that's very close to itself, which influences the person to choose this very far, very inefficient goal. So if you understand how the robot's goal choice influences the human, you can say, okay, actually the robot wants to choose this far away goal such that it leaves the original intention of the person intact. So in our work, we recognize that having an influence-aware prediction model gives us the freedom to choose the robot's objective automatically. So we can specifically utilize our CBP model to switch between these influence and courtesy objectives. And I'll note that this is actually not super typical of existing conditional behavior prediction models. From the literature, basically, they're all thinking about low-level action level influence instead of thinking about high-level objective switching that is a function of sort of high-level influence. So in our work, we take our observational intention prediction, feed it into our conditional behavior prediction model that can choose between a courtesy and influence objective. and finally push this into our safe controller that I won't really talk about here, and output a final action for the robot. So when we run some simulations, basically the first thing we did was compare our model-based CBP method to a learning-based method that's based on architectures from the literature. And the first takeaway is really that having this high inductive bias through our model-based method gives you very similar results to doing this in a learning-based way. So the first thing we do is look at metrics for courtesy, basically how often are you changing this simulated human's goal? And you can see that the two methods are very similar. The second thing we do is measure the efficiency of the team. So how many goals do the two agents pick together through the whole simulation? And we split this here between a very stubborn human that always chooses a single goal and never changes their mind versus an uncertain human that will sort of look at what the robot is doing and choose a different goal if it thinks that the two agents are going to collide. And you can see that both methods are basically capable of interacting with both of these kinds of humans and have very similar performance. And our second main takeaway is that influence-aware robots in general are able to make the team perform much better. So now here we're comparing to two baseline algorithms. First is a naive controller for the robot that always chooses the closest goal to itself. And the second is a reactive goal selection for the robot, where similar to this uncertain human will wait until it knows what the human is going to do and then choose its own goal. So here you can see if you compare the influence-aware methods to the baselines, our influence-aware methods are able to change the human's goal much less often. And similarly, we can do the same comparison for thinking about efficiency. And you can basically see that the naive method is very good at interacting with the uncertain human, whereas the reactive method is very good at interacting with the stubborn human, but sort of each method fails interacting with the other type of human, versus our influence-aware methods, which are very flexible and interact with both kinds of humans pretty well. So we wanted to see if this holds with real people. So we ran a user study with 21 participants where we compared the naive, reactive, and influence-aware controllers. Specifically, we're testing the model-based influence-aware controller because we don't have a big data set in this domain. And we can see some empirical examples of real users being influenced towards efficiency. So here's one user interacting with all three different controllers. So first, you can see when interacting with this naive robot, they're not really sure what to do before they finally pick this faraway goal. And similarly, when the person interacts with this reactive robot, both agents really aren't sure what to do until the human finally picks this faraway goal again. But our influence-aware robot understands that this person might be hesitating, so it decides to influence the person towards choosing this very close goal. And you can see that in the same amount of time, the two agents are able to get much farther in this interaction. And the other cool thing we saw was that our influence-aware controller actually automatically switches its objective based on the kind of person it's interacting with. So on the left, you can see a real user that sort of doesn't know what to do. So the robot is successfully able to influence them to choose this very close goal to them. And on the right, you'll see a video of the robot trying to do the same thing. But in the middle, it sort of realizes, okay, this person is not going to be influenced towards picking this other goal. So I'll just be courteous and choose this goal that's closest to me, and then we can continue on. And we actually see this sort of play out in the overall results of this user study. So when we measure the aggregate results for how many goals were reached for the two agents, you can see that the people are performing pretty poorly with the reactive robot scoring the least goals and hesitating the most, whereas the results for the naive robot and influence-aware robot are reasonably similar. You might actually be thinking like, oh, this naive robot, it's surprising that it performs super well in this task. It actually does the best with people. And this is really because it tells us that people are okay to follow the robot's goal selection in this scenario, but they might not be super happy about it. So we actually asked them a bunch of subjective questions about their preferences on interacting with the robots. And you can see it like across the board that people are not very happy about interacting with the naive robot. So one of the questions we asked was whether they thought the robot accounted for the goal they wanted to pick when they were picking it. Here we're asking Likert scale questions. So basically their responses are whether they agree or disagree with these statements ranked from 1 to 5. So 1 is very strongly disagree, 5 is very strongly agree. So basically people very strongly disagree that the robot accounted for their goal when they're interacting with the naive robot, but they agree that the reactive and influence-aware robots accounted for their goal selection. Another question we asked was whether they thought that they changed the goal that they picked initially because of the robot. And you can see that they do agree that the naive robot changed their goal selections, whereas the influence-aware and reactive robots did not. And finally, we asked people to rank all 3 of the robots in order, and you can see that the highest percentage of people ranked our influence-aware robot as their most preferred method. And as a fun fact, actually, if you treat these rankings as votes for the 3 robots, you can run a ranked choice voting algorithm, and our influence-aware robot does actually win that election. So now I'll talk a little bit about some of the work I've been doing more recently on this full influence-aware safe human-robot collaboration idea. And basically the motivation is that, or one piece of the motivation is that over the last few years, we've seen a lot of success in enabling robots to do really cool things in the real world by learning policies, particularly through reinforcement learning or imitation learning. So on the left, you can see work from some folks at Berkeley where they trained this bipedal robot to run using reinforcement learning, which is super impressive. And on the right, you can see some work from TRI where they're training a diffusion model to do imitation learning for these sort of complex real-world tasks. But one question that I've had is whether these agents or these policies are able to collaborate with other agents. Of course, as a HRI researcher, this is something that I'm really concerned with. So here is a task from this paper called RoboMimic, where the task is for this robot on the left to pass the hammer to the robot on the right. And you can see that when they basically collected the data, they had pairs of humans doing this task. So you can just train a vanilla imitation learning policy on this, and you can successfully hand over the hammer to the other agent. But sort of the bigger question is whether you can robustly collaborate with other agents. So here is me hooked up to the left robot controlling its end effector with the keyboard, and I'm going to see if I can collaborate with this robot. So on the right, it's still using the trained behavior clone policy versus me on the left trying my best to hand over this hammer. And you can see that, like, despite my best efforts, it's actually not able to successfully complete this task and then quickly falls into a space where it's like unrecoverable from like unable to complete this task at all. And it gets even worse if I'm a little adversarial. I can like do something totally random at the beginning, and then even when I go back to trying to complete the task later, the other robot is really not in any state to try and recover from this because it hasn't seen anything like this in its training data. And of course, I am not the first person to point this out. There's been a lot of work in robust imitation or robustifying imitation learning. There's been some work in doing this more theoretically, showing how to use inverse reinforcement learning as a method for robust imitation learning. There's also been some work in the self-driving domain, like this paper from Waymo, on using reinforcement learning in tandem with imitation learning to get more robust policies. But there's a few sort of big problems with a lot of the work that I've seen. First is that they're generally in single agent environments. They don't explicitly consider safety, and they have very strong assumptions on what the other agent's policies will be. So for example, if you have like multi-agent RL, you can do these sorts of interactions, but you're assuming that the other agents have sort of been trained alongside you. And once that assumption is broken, you'll often fail at collaborating with others. So now we're going to look at sort of this full problem of influence-aware safety for collaborative policies that are learned from data. So what do we need to actually solve this problem? One big thing we need is a consideration of other agents' actions. Second thing we want is compatibility with modern learning-based policies. And finally, we would like a safety value function V that we talked about earlier to be automatically constructed for this system. And there's actually been some really cool work recently in doing learning-based Hamilton-Jacobi reachability analysis, where basically you can explicitly account for multi-agent interactions through the disturbance agent. There is deep connections to reinforcement learning because it's basically like a game theoretic version of reinforcement learning. And the whole goal of HJ reachability is to compute the safety value function V of X directly. So in this work, the idea is that we want to use reachability as a method to solve our influence-aware safe control problem. So the key idea in this work was that we want to do this with including the latent intent dynamics into the dynamical system. So we can be robust to the partner strategy without being overly conservative. And specifically here, we can treat the human as our disturbance agent in the game. Our robot is our controlled agent, and each of these has like their own latent intent in their head, where the robot is trying to estimate the human's latent intent. And now we can do analysis of reachability basically over this joint state of the physical state X and the latent state Z. And importantly, the failure set will still be defined in the physical state because we don't know exactly what it means for intentions to be in collision with each other. And then we can do the full reachability analysis with this extended state. So to get a sense of what's actually happening in this learning-based reachability method, I'll step through it now. So first, what happens is you initialize the policies of both agents, basically using single agent reinforcement learning. At each iteration of our training loop, you'll sample one agent, one human agent and one robot agent. You'll have them play against each other. Then you'll update the critic, which represents our safety value function. You can then update both agent policies and then compute win rates, like how often did the disturbance agent drive you to unsafe states versus how often did the ego agent keep you in safe states, and then change how you're sampling at the next iteration. And you can repeat this until you're happy with the trained safety and disturbance policies. So what we are trying to do right now is extend this work to include two key changes. First is the initialization will come now from imitation learning. So basically you'll have some nominal multi-agent imitation learning algorithm that gives you a time step zero policy for the human and robot. And then when you're doing this interaction, we importantly will restrict the set of possible actions that the human will take to the set of epsilon likely actions based on the initial policy. So that's what this constraint set is trying to show here. So UH is picked from all of the set of U's such that the initial policy puts at least epsilon probability on that action. And this is essentially a robust constraint with respect to your initial policy. So instead of saying we know exactly what the human is going to do over time, we'll say we have some set of possible things that we think the human might do, and then we'll allow them to pick the worst case version of that policy and stay safe with respect to that. So this work is very much still ongoing, but here's a preliminary result. Basically, we trained the disturbance policy only using this full interaction loop, keeping no safety policy being trained. And you can see on the left video that if we just have a disturbance that is disturbing the end effector position of this agent, you can still successfully complete the task. So here, the task is just to pick up the block. I'll play this video again. So yeah, the disturbance agent is just perturbing the end effector position, but the nominal policy is still able to complete the task if you're just doing uniform random disturbances, versus if you train the disturbance with reachability analysis, you're able to drive this to unsafe states 100% of the time, which is a great sign. So before concluding this talk, I'm actually going to do something different and think a little bit about further down the line, what can we actually aim for using this full influence-aware safe control idea. So first, I'm going to play a video of some of my friends cooking their lunch together. So we're going to take some inspiration for what happens in this interaction to see what can we aim for in general for robotics, and how can we think about including this in our influence-aware safe control pipeline. So you can see that there's really a lot of coordination happening. There was even a knife in the scenario. So people are very good at doing these kinds of things. And specifically, we saw close quarters, safe, robust, communicative collaboration. And this is something that's really hard for robots to do, especially around people right now. And my hope is that if we think about this full problem of influence-aware safety, we can actually get close to something like this. And just as a little idea, we can point out there was this moment where Alex, who is holding the water, says, hey, Ben, can you watch out? Because he doesn't want to pour water all over Ben's hands. So Ben sort of moves out of the way from the sink. And in the future, I actually am thinking about how we can actually use language to improve safety in this pipeline. So I have some prior work thinking about using language in strategy alignment for a human and a robot that doesn't really think about safety. But the idea was that you can use explanations of strategies between from a robot's perspective, such that you can align the strategies in the future, and then you can be more efficient at the task. But importantly, we didn't think about language at the action level. This was really at a higher level at like explaining full strategies. And we also weren't thinking about safety. So in general, I'll pitch to you that strategy misalignment might actually be unsafe, which is why we might want to use some methods from language generation to improve the safety of this like human robot system. So let's say if these two agents are trying to place blocks, the human wants to put a block at the same position that the robot wants to, and this means that the two agents are actually like very close to being in collision with each other. So instead of just relying on its physical actions to become more safe, the robot might say something like place this on the left, and this means that the person would like get out of the robot's way, and then they can go along completing their task. And you can see that like language was an important part of making the system more safe. So basically what this idea is to extend our full influence-aware safe HRI framework to include physical actions and verbal actions from the robot. So what this might look like is extending the standard interaction loop where we have some ego agent denoted by pi r that has some encoding of the latent intent of the human agent, and then our opponent agent that's just some policy pi h interacting in the world. And then we can extend these by introducing some language models that can output verbal actions for the robot, and then some proxy model for the human that can interpret this verbal action such that it's useful for doing downstream, like finishing the downstream task. So this is basically like, in the future, what we want to do is have some like proxy model that we can train in simulation against, such that we can get the robot to generate like good verbal actions to improve the safety of the system in the long term. Yeah, so that is basically all for my talk. Thanks, of course, to my advisors, Changliu and Andrea, and all the collaborators on the papers I talked about today. And yeah, that's it. Thank you. Yeah. Cool.
So, like, Roy, want to follow up on my first question? Like, are you considering, especially if you were like, almost like some sort of heterogeneous safety for different depends on different humans' preference? Like the act function that depends on like human intent, at the very beginning.
Yeah, so I have not.
Worth thinking about.
Yeah, I think in general, this kind of thing could be worth thinking about. I think for now, I'm just thinking about safety in terms of physical safety. Like you just want to stay out of collision with people or out of collision with particular objects.
It's a very clear definition.
Yeah. And then basically the like hope is that by incorporating the latent attention dynamics, that will influence the safety of the system. And so if you're additionally like changing the safety specification itself based on that intention, I think it just is a little messier, but might be something like worth checking out down the line.
Hey, if you just random stuff.
Sure.
If you presented to Chris Atkinson,
I have not. Yeah.
It definitely bring out like you need to have a safe robot, like something like a Baymax, like hardware safety. Example, like different people have different station values, like I guess preference for different robot, right? You know work with Criticfy, you probably don't even care. But if you work with a very kind of heavy duty sort of like, so
Yeah, I think that's a great point. Like I think there's some other like I guess orthogonal line of work where you could think about how you can specify safety based on people's preferences and then like include that in this sort of overall framework. Yeah.
Any people on Zoom questions? And you just have questions. So,
from that, for the future looks person, like when our humans in the rest of the struggles, we will adapt to the possibility of our that intentions and dynamics that change with time.
Mhm.
So using like learning-based safety. So basically, we are conditioned on some distribution and that human dynamics are also changing. We simply we are to that design method or.
Yeah, so I think really what happens is you'll always have a little bit of a gap between like what you're simulating based on your training data versus what's like actually being rolled out with people. I think there's two pieces to this. First, like your hope is that by doing sort of a robust formulation of safety, you can account for this sort of change in humans' intention dynamics online just by being robust to some full distribution instead of like assuming that the distribution is correct. The second part is like there's some works that's done this idea of like iterative real to sim or iterative sim to real, where basically you'll roll out some simulation of some system and then in simulation and then like roll it out in the real world, see what was different about the actual rolled out policy in the real world, and then include that back into your simulation, retrain. So you could imagine doing something similar to that in HRI, where you're just like rolling out with real people. You see, okay, well, for most of the time you were pretty good at predicting what people were going to do, but like in these few scenarios, it was different. And so you'll go back and change your simulator or like use that data from the people to retrain your initial policy and do something like that. Yeah.
this one.
Yeah.
Thank
Cool.
you. Thank you. Yeah, really close to the art.
Cool. Thank you.
Good way to market and
Yeah.
Yeah.
Great.